Hello again. Welcome to another logic video. In today's episode, we are going to be looking at how to prove an argument using truth tables. And I think this is going to show you some important things specifically about like sort of nuts and bolts of how truth gets moved from the premises to the conclusion. I'm going to assume that you have seen my previous video with the introduction to truth tables to get a basic sense of how the truth tables work and how the operators are defined through a truth table. The operators of the and, or, not, if, then, and logical equivalence. So just as a preliminary, let's quickly review what it means for an argument to be valid. Remember that an argument is valid if, assuming the premises are true, the conclusion must be true, right? In other words, whenever the premises are all true, the conclusion must be true. It is impossible for it to be false. We say that a valid argument is truth preserving. In other words, that if there is truth up here in the realm of the premises, that truth is preserved in the conclusion. It doesn't lose truth. It certainly might mean a valid argument might have false premises, and through accident, we might still have a true conclusion. It might have false premises and get a false conclusion. Those are still possible. But one thing that is never possible is that if the premises are both true or all true, it's impossible for us to get a false conclusion. The truth was not preserved in this situation. As we've talked about all semester, it's something to do with how these premises fit together and what they allow us to conclude. What is the form of the argument, not the content of the argument. All right, so down here, let's get started with this project then. What we're going to do in this video is to prove the 4 different forms we have been introduced to so far: modus ponens, modus tollens, disjunctive syllogism, and hypothetical syllogism. And the largest part of this video will be about modus ponens. I'll spend more time breaking that apart. And then I'm going to go through modus tollens, disjunctive syllogism, and hypothetical syllogism much more quickly, okay? So essentially what we're trying to do is say, all right, when this premise is true and when this premise is true, does it force the conclusion to be true? Is it possible for the conclusion to be false? And for any argument, and you can use this technique for any of the other arguments we're looking at, but these are just the sort of simplest and most bedrock forms that we're looking at, which is why we'll focus our attention here. Okay, so first we're going to set up, and I'm going to do this in the order of modus ponens, modus tollens, disjunctive syllogism, and hypothetical syllogism. In hypothetical syllogism, things are going to get a bit more complicated because now we have 3 different variables, P, Q, and R in hypothetical syllogism, which is going to require an expanded truth table. So after I do DS, I'm going to pause the video, or I'm going to pause the recording, I'm going to build a larger table, and then I'll resume so that you don't have to wait through all of that. Anyway, let's begin, and this is going to have some review as I build this table. So remember when we're building this, so actually what I should say first is that what we want is we want one column with a premise 1. So this column has premise 1. And this column has premise 2. And this column has our conclusion. When we're building a truth table for an argument, I'll tell you what we need is, we need columns for premise 1, premise 2, and a conclusion. And then to help us out, I like having columns for all of the component pieces. So modus ponens is pretty simple because our component pieces are just P and Q. And it's also simple, I'm just laying this out for completeness, but this column with P is going to be identical to this column P. This column Q is identical to this column Q. But as I'm progressing, I'm going to be erasing this everything to the right of P and Q and redoing it for each of our statements. And we'll be using not P and not Q for our later arguments for modus tollens and disjunctive syllogism. Anyhow, to build the truth table, to start off, we're going to start with our P and Q, the simple statements. And to do this, remember, we want a different combination of truth values for each row. And I didn't talk about this specifically last time, but the easiest way to do this is you take your first column and you just take your first half and make them all true. And then you take your second half and make them all false. When we have only two variables, that's 4 lines, so it's going to be 2 and 2. But if we have 3 different columns, 3 different variables like P, Q, and R, that means we're going to have 8 rows. The first column is going to be 4 trues and 4 falses. And I'll show you that when we get to the hypothetical syllogism part. Next, our Q. So if this went 2 and 2, the next one will go 1 and 1. True, false, true, false. Simple as that. Again, if we had 8 rows, this would be 4 trues, 4 falses. And since we went 4 and 4, the Q will go 2 and 2, 2 trues, 2 falses, 2 trues, 2 falses. And then our R column would go 1 and 1, true, false, true, false, true, false, true, false. And that kind of rotation at different speeds for each of the P, Q, and R will ensure that each row is going to have a different combination of truth values in easily recognizable locations, and it will ensure that nothing is doubled up. So we'll have covered everything and there will be no doubling up. So that, in other words, we won't have 2 different rows with the same combination. We're going to skip not P and not Q for now. It's pretty simple to figure out, but we'll skip it for now. Now this column, not if P then Q. Now this is going to be the exact same. We figure this out in exactly the same way as we did when we were defining the operators. In other words, we ask, all right, we say, what is the meaning of this? And it says, if P is true, then Q is true. Is that true when P is true and Q is true? And you might remember that our answer was yes, that's true. If P is if P is true and Q is false, is it true that if P is true, then Q is true? No, because here P was true. We've satisfied the antecedent, but our consequences failed. Therefore, when P is true and Q is false, our conditional is false. Here, if P is true and then Q is true. However, this time P is false. Does that violate our conditional? And it actually doesn't. Remember, this is the confusing one. And if that didn't make sense, this is such an important line, why this one doesn't work, why this one is still true. And when they're both false, is the statement still true? Yes, it is. Again, if that feels confusing to you, and I understand why it might, make sure to review the truth table section in chapter 14 on this. Now, the next premise, the next column is P. So P equals P. So we can just use the exact same column. True, true, false, false. It's identical. Likewise with this, if our conclusion is Q, Q equals Q. So we just use the column over here. True, false, true, false. Right. Now the question is this a valid form? And what are we looking for? So we've already declared that this is valid, but you know, we want to prove it. This is what logic is always about, proving that these arguments are valid. And to prove it, this is what we want to do. Remember what the definition of validity was. If the premises are true, the conclusion must be true. All right. So what we want to do is we want to look at the rows in which all the premises are true. So here we have true, true. Yeah, we want to look at this one because all the premises are true. Row 2, false, true. We don't care about that because not all the premises are true. True, false. We don't care about that. Not all the premises were true. True, false. Again, not all the premises are true. In other words, the only row in which both of our premises are true is row number 1. Now, I'm going to pause here to just mention that with modus ponens, there's only one row in which all the premises are true. That's not going to be the same for all of the arguments. There might be cases where there are multiple rows in which all the premises are true. When we're checking for validity, what we want to do is we want to identify all the rows in which all the premises are true, and only those rows. These rows, because they have a mix of false and true, we can discount them from here on out. It doesn't matter. But once we've identified these rows in which all the premises are true, we check the conclusion column. We're checking the conclusion column, and the conclusion column for all of those rows must have a true statement in order to prove that it's valid. If there is a single case, like if there's a single case where there's a false conclusion, then the argument has been proven invalid, because what that shows is that all the premises can be true, but it's still possible to have a false conclusion. And so long as there's one false conclusion row, the argument is invalid. Okay. So here we do have a couple of false conclusion rows, but again, we don't care because we didn't have all true premises. So what we see here is, because we have two true premises, all the combinations of P's and Q's that gave us all true premises lead us to a true conclusion. Therefore, we can say with certainty that modus ponens is a valid argument. Okay. I didn't think about doing this before, but I'm actually going to show you a case that is invalid. So I'm going to erase some of this. You know what? I'm going to stop the recording. I'm going to pause the recording and clean this up so you don't have to sit through it. That's what I'm going to do for the rest of this. This is my very basic video editing skills. Bam, that was magical, right? So, I'm just kidding, it's very basic. Here's an argument that we've looked at before, and a lot of us declared that this argument was valid at some point. If P is true, then Q is true, and P is false, therefore Q is false. Now, before we understood how this conditional works, a lot of us assume that, all right, if that means that whenever P is false, that forces Q to be false. And we've talked about how this is invalid. So let's prove it. And let me show you what an invalid argument looks like. So again, we have our column if P, then Q. So this looks exactly the same as it did before: true, false, true, true. Now here's our premise 2, which says not P. And not P again is just the reverse of P: false, false, true, true. And not Q is just the reverse of this column: true, false, right? So again, we have premise 1, premise 2, and our conclusion. Now, when we were looking at modus ponens and we asked which rows have all true premises, the only row that had all true premises was the first row. That was true, and P was true, as we see. But now things have changed. The rows in which we have all true premises have doubled. We actually have this row, row 3, and row 4, that have all true premises. So now that means we have to check 2 rows, not just 1. We don't have to check these rows anymore. So now we check both of these rows that have all true premises. We look at the conclusion and we see that in row 3, despite having all true premises, it's still possible to have a false conclusion. Sometimes it can be true. It's possible that the conclusion is true, but it's also possible that the conclusion is false. Therefore, we understand that this argument is not truth preserving. It might accidentally have truth, but it doesn't do anything to force that truth to be maintained in the conclusion. This is what an invalid argument looks like, when we can identify at least one row with all true premises and a false conclusion. Okay. And this is not a form. Remember, we looked at this form. Well, I mean, it is a form, but it's an invalid form, and we don't give it a name because it's invalid. Sorry, that sounds mean, but yeah, we only give names to the forms that are valid. All right, so now let's move on to modus tollens. Okay, like I mentioned before, after modus ponens, I'm going to pick up the speed a little bit. So here I have set it all up for us already. Premise 1, if P then Q, same exact thing as before, true, false, true, true. Premise 2 now is not Q, false, true, and our conclusion line is not P, false, false, true, true. So this is premise 1, that's up here. Premise 2, that's right there. And our conclusion, that's right here. So again, we're going to check the premise rows, or the premise columns, and identify all the rows that have all true premises. So we have true, false, so we don't care about this row. False, true, we don't care about this row. True, false, we don't care about this row. True, true, we care about that row. We're going to check all the rows that have all true premises, and all of them, and by all in this case I mean the one, has true premises, or a true conclusion. Therefore, we have now proven that modus tollens is valid. Again, let's check out this version of modus tollens that people sometimes made mistakes on. If P is true, then Q is true. Q is true, therefore P is true. All right, so I set this all up again. Here we have premise 1. Again, same, I'm going to stop saying that. Premise 1 is the same. Premise 2 is now Q, so that's true, false, and our conclusion is true, false, true, true, false, false. Again, we will check for all the rows that have all true premises. That includes row 1 here. It doesn't include row 2, that's false in both. It does include row 3. It does not include row 4. So now we have to check row 2 and, check row 1 and check row 3. We notice in row 1 we have a true conclusion, but in row 3 we do not. So this line proves that the argument is invalid. All right, let's move on to disjunctive syllogism. All right, so here I just realized I wasn't making use of the not P, not Q columns. I just got rid of those. Here we have disjunctive syllogism. Premise 1 is P or Q. Premise 2 is not P, and our conclusion is Q. So we've set this up here. Here's our premise 1, here's our premise 2, and here's our conclusion. So premise 1, again, we're going to identify every row that has all true premises. In this case, it's not 1, it's not 2, it is 3, it's not 4. And so we're going to check row 3, true conclusion. Therefore, we know that disjunctive syllogism is valid. Let's finally move on to hypothetical syllogism. Okay, so I started, because we were expanding the chart now, I reoriented, rebuilt a lot of this. But hypothetical syllogism, again, if P then Q, that's premise 1. If Q then R, that's premise 2. If P then R. So like I was mentioning before, I talked through it, but I'm going to show it to you this time. When we increase the number of variables, we need to increase the number of rows as well. And to determine how many rows you're going to use, we take the number, essentially what we're doing is taking the number of possible combinations for each one and multiplying it. 2 times 2 times 2. This essentially means that you're doubling the number of rows every time you add one variable. So if there was only one variable, there's 2 combinations, true or false, you only need 2 rows. With P and Q, you need 4 rows. With PQR, you need 8 rows. For some reason, I keep having students tell me 6 rows. It's not 2 plus 2 plus 2. It's 2 times 2 times 2 times 2. And if that means that if you had 4 variables, you would be at 16 rows. If you had 5 variables, you'd be at 32 rows. This is essentially how computers think. It takes a lot of very small data points and works through them very, very quickly. Human being, like, just as a side note, one of the things we're doing, like, this is using truth tables is not the method we're ultimately using in this class. We are doing what we call natural deduction by going through the proofs and using these rules one by one. But this is a kind of mechanical way of showing this. That other thing that we're doing takes like creativity, and it's a much more difficult thing for computers to be able to do, much easier for humans to do. But we have to use a sort of like deeper level of our intelligence. Anyways, moving back to this, now that we have 3 different variables, we have 8 different rows. Again, the first column, P, we're not going to do 2 true, 2 false. We're going to go 4 and 4 now. So that's true, 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 false, 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 false. 2 trues, 2 falses, 2 trues, 2 falses under Q. And then under R, it's just true, false, all the way down. Okay. Now, here we have if P, then Q. Now remember again, we're not just repeating the form that we saw on the 4 row version of this. We are always going back here and asking, is if P then Q true? When P is true and Q is true, yes. But now we still see both of them are true. So it goes 2 trues. Now we have true, false, 2 falses, then false, true, that's true, and true. What you do notice is that the proportion is the same. So before we had 1 true, 1 false, then 2 trues. Now it's like that's doubled, just like over here everything's doubled. So it's still 1/4 truth, 1/4 false, 1/2 true. So that's just something to get used to. Now this is going to be a little different. If Q then R. Now over here, this is a little different. Actually, this is going to look more like the P and Q before. True, true, that gives us true. True, false, that is false. False, true, that is true. False, false, that is true. We're going to see it repeats now. True, true, that is true. True, false, that is false. False, true, that is true. False, false, that is true. Now here's, I think this changes a little bit again. If P, then R. So we're looking at true, true, that's true. True, false, that's false. True, true, that's true. True, false, that's false. False, true, that is true. False, false, that is true. False, true, that is true. False, false, that is true. Okay, so it's interesting to note that we still have, in all of these, we had 2 falses, 2 falses, 2 falses. There's always 2 falses and 6 trues on these conditionals when we're just doing it off of the basic simple statements. But where they're located changes. Okay, so you just have to figure it out every time. It's the most sure way. Once you've been doing it a long time, you kind of see these patterns. But that's not as important right now for y'all. Moving on. So just like before, we indicate, we identify which columns are our premises. So if P then Q, this is premise 1. If Q then R, this is premise 2. And our conclusion, if P then R. And again, we're going to identify all the rows where all the premises are true. So just looking at the premises, true, true. Yes, we care about this. True, false, no, we don't care about this one. False, true, we don't care. False, true, we don't care. True, true, we care. True, false, we don't care. True, true, we care. True, true, we care. So when look at all the rows in which we have all true premises. This is row 1, row 5, row 7, and row 8. And we want to make sure that every single column, every single conclusion for those rows is true. And indeed, we see that, which means that no matter what combination of all these 8 combinations, whenever the premises are true, not necessarily the simple statements, but whenever the premises are true, we always get a true conclusion without exception. In other words, for our argument, when the premises are true, the conclusion is necessarily true. This is valid. All right. Well, that concludes this video. I hope it was helpful. I hope it shows, like, you can use this method now for more complicated arguments. It doesn't matter which argument you plug in. All these ones that we are proving in our exercises and on our quizzes, assuming you fill out the chart correctly, you could use this method to prove the validity of any argument. I'll also note, and I'll have to say this later at some other points as well, but using the natural deduction method that we are going over in chapters 18, 19, and beyond, there's no way to prove those arguments are invalid. You can only prove the arguments are valid. And if you haven't been able to prove that they are valid, that doesn't mean that they're not valid. Maybe it just means you haven't found the solution yet. That's a very different kind of process. Here, you can prove that they are valid. So in some ways, the truth tables are more powerful. In other ways, just because it's like it's a much slower, more grindier mechanical process, this becomes very burdensome compared to the natural deduction method once we learn what we're doing there. But in a way, this is like the truth tables are essentially solving the same 5 problems again and again and again and again and again. And so long as you don't make any mistakes, you'll get to the right answer. It's just the problem is that because there are so many more steps, the chances that you make mistakes and can identify those mistakes when you make them, it just becomes a much more error-prone situation, unless you're a computer. Anyway, that's all for today. Have a good weekend, and I'll see you on Monday.